In this video, we'll give a brief introduction to the mathematical ideas of chaos and what this looks like when you actually see it show up in a physical system. So if you've heard the idea of chaos before, the thing that probably comes to mind is the idea of the butterfly effect. And so this is the idea that's been formulated for a while. It basically says a butterfly flapping its wings on one area of the world can affect the path of a tornado somewhere else entirely. Well, this is slightly, exaggerated in how things like this can actually work. The idea here is actually pretty relevant. And so what does this look like from a mathematical point of view? Well, it's not like this is unpredictable, but it's not like we can't model what happens and see this can happen over time. In a mathematical sense, chaos is always predictable because differential equations always are. These are all deterministic equations. There are things called stochastic equations that are random in nature, but we're not doing that. That's way beyond this course. But it's always predictable. We can always say, given a starting point, we know where we're going to get to. However, what makes chaos interesting to think about and how mathematically we define chaos is that if a differential equation or system is chaotic, it means that the system has an extreme dependence on initial conditions, or is a non-continuous dependence on initial conditions. And what we mean by this in terms of this extreme dependence is that if I make a very small change in initial conditions, like just a tiny little change, I get large differences in solutions as we go out further in time. So even though they start really close together, they end up really far apart. So a small change in initial conditions leads to a large change in the solution in long term. That's sort of the key point here. And we'll see this comes into play a little bit later. We'll get to the guy who sort of made this assumption or this conclusion later on. But the main idea that he found was rounding his initial values caused wildly different changes in the prediction of his model. And so even just a rounding error at like 3 or 4 places out caused a long-term change. So let's start by looking at some non-chaotic behavior and compare it to what happens later. So here we have a system that is very much non-chaotic. We have y double prime plus 0.2y prime plus y equals 0.3 cosine t. We sketch out two different solutions for different initial values and see how they compare over time. We get this picture. And now for this, we kind of already knew what was going to happen, right? What is this system? Well, this system is a damped forced mass on a spring, right? We have our y double prime, we have our damping term, we have our constant term, and then we have our force term on the other side. This is a damped forced oscillator. And so we know how these work. We know there's a transient part, there's a periodic part, and over time, the solution tends towards a steady periodic part. So it's going to converge to that thing. That's the red graph in the bottom right. That's a steady periodic part. So what you see here are two pictures. The first is two plots drawn for the first 20 seconds, I guess, of time. And then the same plot drawn further out from 60 to 100. And like we saw when we did this step the first time, they start different. There's a transient part that's the difference between them. But over time, these things converge and land on the exact same steady periodic solution that we're going to see further out. That's based on the non-homogeneous part of the problem and all that stuff that we've done before. If it was undamped, you'd see a sort of constant difference. But with the damped case, they converge to the same steady periodic part that we're going to see at the end of the problem. So this thing here is the steady periodic part. And all solutions, no matter the initial conditions, converge to the same solution. All right, so that's what happens if we don't have chaos. Now, what happens if we do? So here's our new system. I'm intentionally not showing you the graphs yet. So we have something that looks pretty similar. We've changed two things. One, we've changed this to a minus y. So it's not really a mass on a spring anymore. This actually fits more of what's called a double well potential in physics. And we've added a y cubed nonlinear term here. The two is going to give me the double potential. And so now we're going to draw two different solutions. One that starts at the point 3, 3 in terms of y and y prime, and one that starts at 3 and 2.9. So all we've done to change is we've changed that 3 in the velocity to a 2.9. If we draw the starting part of the solutions, here's what we see. This is the same window from 0 to 20, right? For the non-chaotic case, we saw these things sort of converging closer and closer together as they went on. But here you can see something weird's happening. After a while, the lines almost overlap at the start, but after a while, you start to see the blue one poking out separately, and they seem to be going on slightly different trajectories, right? The blue one picks up earlier and dives down earlier. Things are getting a little strange here. It gets even stranger when we go further out. But now we're going to look at the same graphs, just plotted instead between 50 and 100 instead of 0 to 20. And that's what we see. These graphs are not even close, right? They're not even showing the same behavior. They're showing weird things in different spots. The peaks are in different spots. The valleys are in different spots. The flipping over is in different spots. Everything is different from these two solutions. And for this, we just started from a velocity gap of 0.1. These are even smaller. It takes longer to get to this chaotic behavior, but it doesn't matter how far apart you start. You make a small change in velocity or position, and you're going to get this kind of difference further out. So to show the full picture, these are these graphs drawn on top of each other. Again, you have the blue at 3, 3, and the red at 3, 2.9, and you see that once you get even beyond a little bit further out here, these things have almost nothing to do with each other. So a very small change in the initial velocity caused a distinctly different behavior in the solution as we go further out. And these aren't just numerical errors. We had to use numerical methods for this to solve this because we can't solve this by hand. There are a lot of steps of the method here to make this be fairly accurate. So a small change, we went from y prime of 0 being 3 to it being 2.9, caused a substantial change in the behavior of the solution. They're not really close, jumping all over the place, and they are different from each other, and that's the important thing. Not that these are crazy. Crazy solutions are fine, but these are different even though they started super close together. And that's the idea of chaos, at least from the mathematical point of view. It's that if I change something by a little bit, I get a big, big change later on. This is mathematical chaos. Now we can go into the original example of this and where this came from, and it's actually weather. So Lorenz is the guy who first came up with this idea of chaos when he was trying to write a system to model the weather. And what has been proven since then is that a system has to have at least 3 components to have chaos involved. It's going to be autonomous. It must have at least 3 components. And a model that he developed for looking at the weather was this set of 3 equations here. I don't know where they came from. They came from somewhere, but they is what they are for a certain type of weather phenomenon. And you have them here. This equation is almost linear, right? We only have a couple terms here that are off. We have this xz term here, and we have this xy term down here. Otherwise, it's basically linear. A couple nonlinear components, that's all we've got. However, this is where he noticed that changing how he rounded the initial conditions caused distinctly different behaviors in what his model said was going to happen in the future. And this was concerning for obvious reasons. And so we got looked into a lot more after that point. So what we're going to do for showing this, we're going to draw 2 different solutions, one with initial values 3, 3, 3, and one with 3, 3, 3.1. And if we do that, we see something quite similar to what we saw with the previous model. The plots here are of the x component of the solution, so these are both x of t, x of t. So what we see is, again, at the start, because they start close together, they stay close together for a while. But then we get in here, and at around like 4 or so, you can start seeing the blue being a little different, peeking out differently, doing a different behavior than the red. That starts getting really, really bad by around 9 when they actually dive opposite ways at that point. And again, the z component started 0.1 off between these 2 solutions. They dive different ways, and if you go further out between 30 and 50, it's chaos. And I mean that both literally and figuratively. These things don't look really like at all. They're all doing different things. They're going different ways, right? You can see sort of in this area, the red one has like, 4 humps in a row, then it takes off, whereas the blue one's just like bouncing up and down like crazy over here. The blue one has some humps in here and then jumps up and down again. And they're just doing random things in random orders. They're not same as well. I won't say random because it is predictable. You can say what's going to happen, but being off by 0.1 on your initial value gives you a very different picture of what's going to happen for this system. Everything's going to be different depending on where you start. Now for this system, let me go back to the equation itself. You could go through the whole process of figuring out equilibrium solutions, linearizations, all that stuff. You can do that. That's not too hard to do for this sort of system here. You can linearize and see how it all works. But that doesn't give you the whole picture. There's a lot of weird stuff going on with the shape because of the fact that there's a chaotic behavior going on here. And we'll talk about that by going to this picture here. So this here's what's called the attractor, or the strange attractor for this system, or it is a model of it. This is me plotting that solution that we had, this x of t from before, the blue one, in 3 dimensions. And if you notice here, we're not really seeing a saddle or a spiral or anything like that. It's sort of bouncing around between these 2 different or sort of halves of this butterfly attractor here of this thing and going back and forth forever in weird random ways. And this is why you get these sort of weird behaviors out of this, right? One half here is when it's doing the humps at the bottom. The other half is when it's jumping up to the top. And it gives you a weird picture here. It's not a spiral. It's not a sink. It's nothing that we've seen before from linearizations. There's a distinctly non-linear behavior going on here, which is this idea of chaos. So this weird behavior cannot be seen in linearization alone. You only get this out of the non-linear interactive behaviors of this sort of system, as well as the weird way it's built to provide this sort of chaotic result. Which really goes to show that, yes, linearization can do a lot, but it's not going to cover everything. And so this is sort of a case to be aware of when you're trying to model something that gets some numerical solutions in there too along with your linearization. So you can put the 2 together and get an idea of what's actually happening to the system. And just to wrap up, we'll go back to the solution for the Lorenz system again, all the way from 0 to 50. You can see the beginning where it looks like it's all going to be nice and just steady, grow periodic, and then chaos happens and this goes everywhere. So what we can do about this? The answer is not much. It can happen. It's rare, but it can happen in certain situations, and it's something to be aware of when you start trying to, model things in the real world, that things can be weird, right? This is a system model of the weather, and it's just chaotic. And no, this is not necessarily why weather forecasts aren't great. This is long-term stuff. But something to be aware of, that modeling physicals in the real world can cause weird behaviors beyond what you might expect to happen normally. And so it's good to have a balance of the theory, the numerics, and the physical modeling to make sure everything comes together and gives you the right result you're looking for a system like this. So here's the idea of chaos. It's pretty cool. Does a lot of weird stuff. It's something to sort of just be aware of as you go forward to do modeling problems in the future.